So this is a tutorial video for Monday, May 3rd. We're talking about the exchange of energy in the form of motion. We're going to be talking about this for a number of days because there's a number of ways that we can describe and talk about motion. The first way that we're going to talk about it is today is speed. Speed is a relationship between a distance and a time it takes to cover that distance. We see the speed of a number of different animals and activities related to Usain Bolt's sprinting speed. Like I said, a speed is a distance divided by a time, or the relationship between the ratio between a distance and a time. The faster something is, the more distance it will cover in the same amount of, time compared to something that's slower. We describe speed in a number of ways. One of the set of units we're used to seeing it as is kilometers per hour. Another one we've probably seen would be meters per second. But we can use whatever type of thing we want to compare in a ratio. When we're talking about the tectonic plates, they might move at a rate of centimeters per year. We might see that type of speed ratio, things that are moving really slowly. So we use this equation, which is distance divided by time. We use this equation to calculate speed. It says here average speed, and that's because it's tough to keep a consistent or uniform speed. If we think of different things that we do, whether we're running, our speed varies. If we're driving, say from Fort McMurray to Edmonton, it's okay, Jetson. It's okay, Jetson. That's my puppy having a bad dream. If we're driving from Fort McMurray to Edmonton, we might even set the cruise control, but our speed will vary slightly. We might slow down or speed up to get around a vehicle. So average speed is a distance divided by a time. So it's a relatively basic formula. We're going to do a couple examples here. A student walks 30 meters down the hall in 1.5 minutes. Find their average speed in meters per minute. What is this in meters per second? So we look to see what we're given, and it usually looks helpful to see the numbers and the type of units that they're describing after. We have 30 meters, that's our distance, and we have 1.5 minutes. So speed is equal to distance divided by time. 30 meters divided by 1.5 minutes ends up being 20 meters per minute. Now, 20 meters per minute, that's an acceptable way to have an answer. This asks for it also in meters per second. Meters per second is something maybe we would see a little more commonly. So if you're traveling 20 meters in a minute, you're going to travel less meters in a second. So we need to multiply it by a conversion factor of 1 minute over 60 seconds. When we multiply that conversion factor, that has the effect of canceling out our minutes, because we have a minute in the bottom and top of a denominator. And 20 times 1 divided by 60 ends up being 1/3, or 0.333 repeating meters per second. A second example has us bring in our use of scientific notation. So a huge ocean wave or tsunami travels a distance of 4 times 10 to the power of 6 meters in 3.6 times 10 to the power of 4 seconds. Calculate the average speed of the tsunami. So to do this, we need to convert to standard notation. Our formula is going to remain the same. Speed equals distance divided by time. To convert our distance, which is 4.0 times 10 to the power of 6, we remember that we just need to move our decimal place over as many times as there are that exponent, because we're almost multiplying it by 10, multiplying it by 10 6 times. So we would move it over once, twice, 3 times, 4 times, 5 times, 6 times to make, this would be 4 million. So our distance is 4 million. That's meters. And that's divided by a time. Well, our time is a lower exponent, 3.6 times 10 to the power of 4. So 3.6, move it over once, twice, 3 times, 4 times. That is 36,000 seconds. 3 seconds. So we have our numbers to punch into our formula. We have 4 million meters divided by 36,000 seconds. And what that ends up being is 111.111 repeating meters per second. So we'll get questions that will give us different parts of the formula. So this first one, or the easy one, we're given distance, we're given time, we don't have to manipulate anything. This next question we're going to do, we're given the speed, we're given the time, and we're looking for distance. So we're given a speed here of 6.9 meters per second, and it's going to be traveling for 4 seconds. So it's helpful always to write our formula. We need to get this distance by itself. We need to get this distance by itself. Right now the distance is currently being divided by the time. To get rid of that, we need to multiply or do the opposite of divide by t, and that will be multiplying both sides by t. Why we do that? Because t divided by t cancels. That would leave us with the distance by itself. And so the distance, or speed times time, is equal to the distance. You can do this manipulation before to your formula. You can do the manipulation when you get the numbers in there. It's up to you. But now that I have my formula rearranged, I have a speed, 6.9 meters per second. I'm multiplying that by a time, 4.0 seconds, and that will give me my distance. And that makes my distance 27.6, and it'll be the same units as my speed, meters. Once again, you could have put these two numbers into your original equation and then done the algebra, or you could manipulate your equation before, but here is your answer. The last practice problem is where you're looking for time. You're given speed, you're given distance. This one's the toughest one for people. And why it's the toughest one is because when this formula starts out, our time uh, is in the denominator. It's dividing the distance. So we need to get time by itself. We need to get time by itself, but we also can't have it in the denominator. So we can do the same thing we did in our last problem to get rid of time from the denominator here. And that's multiply both sides by t. What that does, t divided by t cancels out. You now have s times speed times time equals distance. We have to do one more thing we have to move, and that's to get rid of speed on the left side. Because speed's being multiplied by time, to get rid of it, we do the opposite, which is division. We do division because it is, again, the opposite of multiplication. Speed divided by speed cancels. So time is equal to distance divided by speed. If we look back to our original equation, one way to, if you're thinking of that, maybe a shortcut to remember is when we're looking for time, we have to we end up switching it with speed. Speed becomes our thing that we're dividing our distance by. But once that's done, we have the formula that we can use. So we have a distance, and that is the distance around the planet, which is 4.0 times 10 to the 7 meters. Let's write that out. 4, and when I move my decimal place over 7 times to the right, 1, 2, 3, 4, 5, 6, 7. I'm dividing that distance, which is in meters, dividing it by my speed, 694 meters per second. Yeah, punch that in my calculator. That time ends up being 57,636.89 seconds. So that is a lot of seconds. It would be about 16 hours. Which is still a lot faster than that many planes of the time could do. If I wanted to convert that to the least amount of significant digits, which is 3 for this problem, I would need my question to end up looking like this: 5.76. The 3 would round down, times 10 to the power of however many times I'd have to move my decimal place to the left to get there. 1, 2, 3, 4. So it'd be times 10 to the power of 4 seconds. This would be your answer in scientific notation to the appropriate amount of significant digits, which is 3. The last thing I'm going to talk about is distance versus time graphs. When we represent distance in a ratio to time in a graph, we're able to see certain features in how that data displays on a graph. Time is always our x-axis. Time is always our x-axis, and distance will be our y-axis. Let's look at a couple different lines and talk about what's happening. So as time increases, distance increases. And if we compare the red line here, over a certain amount of time, this distance increases a little bit versus the same amount of time, and this green line, the distance increases quite a bit. Uh, we can use a distance versus time graph to calculate the speed of an object. If I wrote in some times here, so this can be 3 seconds, and this can be go up by increments of 10. As most of us have done, or I'm hoping are doing in math right now, work with slope. If we calculate the slope of any line, we can calculate the average speed of an object. Let's look at the green line. The green line, it travels a distance of 70 meters in 3 seconds. So our rise is 70. Our run is 3. That 70 would be in meters, the 3 would be in seconds. It ends up being 23.33 meters per second. When we talk about that red line, it goes up 25 meters in the same 3 seconds, and that ends up being 8.3. So these speeds were calculated just by finding the slope of the line. And to find the slope of the line, you find a change in y divided by a change in x. The steeper a line is, the faster an object's going. When something is going a steady speed, we're going to see a straight line. In a distance versus time graph, when we see a flat line, that means that something's not moving. If we follow the red line here, we have some movement, our distance is increasing while our time increases, and then all of a sudden at 3 seconds, our time is continuing to increase, but our distance is not. So stationary requires a flat line. When something's getting faster on a distance versus time graph, we see a curved line. So if we follow the blue line here, in the first 3 seconds, it travels 10 meters, or maybe 11 meters. But then in the next 3 seconds, it travels from about 10 to 35. So it's traveling then at about 10 meters per second. If we look to the next 3 seconds after that, we go from about 35 to 70. So this is an object that's speeding up, and we require a curved line when something is speeding up. Finally, in a distance time graph, when something is returning to the starting point when you see a downward slope. So we're following our red line from before. It's going at a steady speed until time is increasing, but distance isn't, so it's at a stop. And then time is increasing still, but distance is decreasing to a point back to 0. So we need to see if it's returning to starting point, a downward slope. I'll get you to pause and maybe describe this section here on its own, on your own. This graph, we start at 0. We start at 0, and as time is increasing, distance is increasing. So this thing is traveling at a steady speed. We can say that it has a steep line, so it's going quickly. At point B, time is increasing, but distance is not, so it stops. And then C, that we have a downward slope. It's a gentle slope, so we can say it's returning slowly. So there are a number of pages that we can practice our interpretation of distance versus time graphs. Please don't go, you don't need to go any further than page 6 because we'll start page 7 tomorrow.